So welcome everyone. Thanks for joining me here today. My name is Tobi Ajila, and today I'll be talking to you about virtual threads. So before we get started, I should point out this session was originally proposed by one of my colleagues, Anamika Roy Chowdhury. So she wrote the abstract, made the title. Unfortunately, she wasn't able to attend, so I'm filling in for her. So a little about myself. I'm a JVM developer for OpenJ9 JVM. And I mostly focus on the runtime aspects of the JVM, so the internals. In the past, I've worked on checkpoint restore technologies, Project Valhalla with the valid text prototypes, and Project Panda. I've also done some work with virtual threads internals. So for this presentation, I'm giving this from my perspective, from a JVM developer. I will go over the basics and the APIs, et cetera, but I'll be looking at it from a JVM perspective and touching a bit more on performance aspects. So like I said, I work on the OpenJ9 JVM team. So OpenJ9 is an open source JVM. It was open sourced in around 2017. But it's been around since the late 90s. Previously, it was a closed source distribution by IBM. Since being open source, OpenJ9 is the open source name, and Semaru IBM is the IBM branded name. But all the development is done in the open, so it's very easy for users to interact with the developers and make requests and things like that. So yeah, there's some links over there. So today we're going to look at Java's legacy threading model, discuss how it works, what are some of the drawbacks, and then we're going to look at Project Loom and how it addresses it, and we'll talk about virtual threads in particular, and take a look at how those perform with real-world applications. And then towards the end, I'll briefly touch on structured concurrency and scope values, because these features round out the Loom support. All right, so as you probably all know from your OS class, a thread is a unit of concurrency. On multi-threaded systems, you can use threads to express concurrent or parallel computations. So this is what helps you make the most use of your CPU resources. It helps you increase your utilization of a CPU. It also helps with responsiveness. If there's an event coming, you can just make a thread to wait on it and then respond immediately once the event's fired. It also helps with scaling. As the load increases, you can scale the number of threads. You're limited to the number of CPU, of course, but it helps scale to meet the demand. So in general, multitasking is a good thing. I don't think I've heard anyone say a negative thing about the ability to multitask in a computing sense. So with business logic, given these beneficial properties, there's been a large adoption of the thread per request style of programming, where each request is handled by a dedicated thread. So the benefit is that this model is very simple, or relatively simple to write, but it's very simple to reason about because you have one task, one thread per task. So now we're going to look at how threads work in the JVM. So here's a simplified diagram, but I think it gets the point across. So at the top, you have your Java-lang thread. So this is what you're interacting with when you're programming. This is what you call thread start after passing the runnable to. Internally, there's a representation of the thread in the JVM. The JVM has an abstraction over the OS thread. You can think of it as a wrapper over the OS thread. So the JVM needs to append some state to the OS thread to track things like interpreter and JIT state, things like metrics for MX beans, for example, often added there. And it's also important for thread handshaking. So when a GC runs, it needs to be able to control a mutation in the Java heap, and it has to be able to pause threads. So keeping track of all that state for handshaking is also stored there. And then at the bottom is the actual OS thread. So think of P threads, for example. So these are the threads, the underlying threads that the JVM is using. And of course, these are the OS threads are scheduled by the OS scheduler, and that's what runs on the hardware. Now, there are some limitations with the legacy model in Java. You'll notice in the previous slide, we have a one-to-one relationship from one-to-one with the Java thread to the OS thread. So this causes some issues. First of all, OS threads are slow to create. When you think about what the OS has to do to spin up a new thread, it has to allocate memory for the stacks. There's a lot of bookkeeping with the scheduler. So it does take time to create a new OS thread. So if you want to use the thread per request model and you're excessively creating new threads, you will often pay for the overhead of spinning up new OS threads. And so this can often cause poor performance due to CPU and memory usage. The more threads you have, the more context switching you have to do, and this can be a costly operation, anywhere from 10,000 to 100,000 cycles, depending on your operating system and the number of cores. Also, the OS is limited in the number of threads it can create. We're looking at the thousands level. So if you have a lot of tasks you want to run, you might hit an upper bound on the number of tasks you can create. So due to these limitations, a lot of people have moved away from the thread per request model and are now using async or reactive approaches. So it's essentially where you have an event loop instead of creating a thread per request. So you run multiple event loops on each of the CPUs, the cores, and then assign tasks to those. So overall, this approach scales very well. It performs very well also. You've essentially taken out the OS context switching and the overhead of spinning up new threads. But the big drawback is that it complicates the model. It's no longer a simple thread per request model. You have to do something a bit more complicated. There are other approaches that involve using thread pools, but the issue with a fixed thread pool is as soon as one of the worker threads has to block, you've taken a unit of execution out. So, for example, if you had 4 threads in a thread pool, 2 of them are blocking, waiting for something, now you have half the throughput. So if you're using this approach, you have to combine it with a mechanism that scales when you're blocking. So these are some of the workarounds that have been developed in the industry. Some of these APIs like Springboard Flux, Vertex, quite popular and quite used extensively. So what we really want is the simplicity of a thread per request style of programming. And ideally, we don't want to pay the performance cost of creating a new OS thread every time. So fortunately, this is a bit of a solved problem. There's a concept of user space threads that have existed for quite some time. In fact, in the early days of Java, there was something called green threading, where you could map multiple Java threads to a single underlying JVM thread. So essentially what this does is it allows you to create a thread in user space and schedule it in user space. So underneath it, you're still just using one thread. Other languages have done something similar. So C++ has fibers, Go has Go routines, Kotlin has coroutines, and there's others. So with Project Loom, the JDK is introducing user space threads called virtual threads. And this allows users to continue to use the thread per request model. So Loom is composed of 3 components, so virtual threads. This is the main piece. And then there's structured concurrency. So this is a programming model that is aimed at enforcing simple concurrency model that allows you to manage concurrent tasks. And then there's scoped values, a mechanism used to pass data between function calls without adding it to parameters. So all of these three are distinct features, but they all work together. So we'll start with virtual threads. So the limitations of this feature is to, the purpose of this feature is to remove the limitations with making many threads. So typically with Java-Lang threads, you're limited to the order of thousands before you start to see some kind of degradation or a hard limit from the OS. But with virtual threads, the intention is that you'd be able to make millions of these and not suffer great performance loss. So the goal is to make them cheap and not resource intensive. So before we get started, I'll introduce some new terminology. So for the purposes of this presentation, and I think this is official terminology now as of JDK 19. So the legacy threads are now known as platform threads. So when you think of threads pre-Loom, those are platform threads. And then virtual threads are the new lightweight threads. And then carrier threads are a special class of platform threads. They're identical to platform threads, but their sole purpose is to act as worker threads for the virtual threads. And we'll see how those interact. So here is a similar diagram to the one you saw earlier. So on the left, we have the platform thread with the one-to-one relationship with the OS thread. And on the right, you have a carrier thread, which is identical to a platform thread, one-to-one relationship, but its purpose is to run virtual threads. So when you think of how an OS thread can be executed on a CPU core, and you can have many OS threads executed on fewer CPU cores, it's the same kind of concept here, where you can have many virtual threads executed on fewer carrier threads. So let's take a look at how you can use these. So over here we have an example of how you can write code to create a virtual thread. So the thread API has been expanded to include a thread builder. And so you can get access to the virtual thread builder and then supply it a name and then start giving it a runnable. So it's very similar to what you can already do now with the legacy threads. There's a shorthand for this where you can just start the virtual thread. This builder pattern is not limited to virtual threads. You can also do the same with platform threads. So the only thing you have to change is of platform, and then the rest is the same. So it's fairly straightforward to make use of these. So here's the type hierarchy. So at the top, we have Java-Lang thread. And then, so Java-Lang thread is what the platform threads are. And then beneath that is an abstract class called base virtual thread. And what this does is it adds the park and unpark APIs, which is used internally to control how virtual threads are mounted and unmounted off of carrier threads. And then beneath that, you have the virtual thread type. And then there's a bounded virtual thread. So bounded virtual thread, for the most part, I don't think any developer will interact with this. It behaves similar to a virtual thread, with the exception that it is backed by a OS thread. So the real purpose for this is testing. For the most part, we're only dealing with virtual threads or the Java-Lang thread. Right, so given that virtual threads are a subclass of threads, they inherit all the methods. However, the methods don't behave the same in all cases. So stop, suspend, resume is not supported with virtual threads. It throws an exception. And as of JDK 20, I believe this is also the case for platform threads. So those are no longer supported. setDaemon throws a legal argument exception with virtual threads. A virtual thread is always a daemon thread, so that property can't be changed. And then the priority of a virtual thread is always normal. So if you try to change it, it's a no op. Thread group always returns the virtual thread group for virtual threads. There's a new abstraction for a collection of virtual threads. The internal mechanism is called a thread container, but this is exposed via a shared thread container or a thread per task executor. And then things like get all stack traces only return platform threads. The reason is that because virtual threads are quite numerous, the way virtual threads are managed is different. With platform threads, the VM internally keeps a list of all the platform threads. But if you have 1 million threads, then keeping a list of that becomes very expensive due to synchronization, et cetera. So in order to get all the stack traces of all virtual threads, you actually have to do a heap walk and find all of the virtual thread objects. And so this can be a very expensive operation. So for this reason, APIs like get all stack traces will only return platform thread stacks. And then there's a helper here to query whether the thread you're currently dealing with is a virtual thread or not. Okay, so we'll take a look at a bit more of the internals of virtual threads. So there are 2 core mechanisms that are used to support the virtual thread functionality. The first one is continuation, and the second one is scheduler, more specifically a user space scheduler. So a continuation is an abstraction of control flow that represents execution state. So think of it as everything that captures the activity that's going on in a thread of execution. So the stack, the locals, what's in the registers, et cetera. So a continuation captures that state, which allows it to facilitate context switching. So you can pause state and then resume state. In Loom, however, we're dealing with delimited continuations. So these are not full-blown continuations that capture the entire memory that's available to a state of execution. It's a limited capture. So it gets part of the stack, part of the entire state. And then the scheduler, so Loom uses fork join pool as the scheduler. So this is a work-stealing scheduler. It's used in other places in the JVM, in the JDK, that is. It's also used with completable futures and with parallel streams. So this schedule is unique in that each worker maintains its own list of tasks. So each worker is greedily trying to add tasks to its own list, and then it operates on those. So it uses a divide and conquer approach, which is generally suitable for executing many small tasks. So here's a little diagram that shows how it works. So you have the fork join pool scheduler, which has a number of carrier threads. Now, typically, the number of carrier threads will be equivalent to the number of CPUs. However, there is a property that you can use to change this statically at startup time if you want. So each carrier thread is executing a single virtual thread at a time, and all the other virtual threads are effectively just waiting for their turn. So if we look at this example where we have code that's using a reinitiate lock, so we're starting a virtual thread, and so what happens is that when you start a virtual thread, a virtual thread is created, and then before it can run, it has to be mounted onto a carrier thread. So the act of associating the virtual thread with the carrier thread is what enables it to execute. And so the term for this is mounting a virtual thread onto a carrier. So once that's done, it then executes. And as soon as it reaches a blocking point, so this is a point where the virtual thread has to wait for something to occur, then the virtual thread is unmounted. So internally it's calling park, and this is what removes the virtual thread from the carrier thread. And then the carrier thread is going to go away and look for another virtual thread to run. So in this case, we're hitting a lock. The lock is held by another thread, so we're going to block. So once the lock is free, the virtual thread is added back, and it's mounted again onto the carrier. So in this case, unparked, and then it's a continuous execution. So the way this works is internally, the virtual thread makes use of the continuation to pause and resume state. And as I said earlier, the continuation is composed of the things that make up the execution state, things like the stack, the locals, the CPU state, etc. The continuation is a unique structure in that it kind of lives in between the Java heap and the JVM. So the continuation type itself is a Java type. However, it refers to the internals of the JVM and keeps track of these things. So when starting or resuming a virtual thread, what's going on internally is that the continuation is entering execution, and this is what facilitates mounting the virtual thread onto a carrier thread. And then blocking is when the continuation is yielding, so it's yielding its execution. So we're going to look at how this works. So when a virtual thread is mounted, initially you'll have a virtual thread somewhere on the heap. If it has been executing before, so if it has been started already, it'll have state associated with it. So I have a little stack there to represent that. But if this was a new thread, there'll be no state. So the act of mounting the thread involves basically taking that state and putting it on the carrier thread. So the carrier thread is a regular Java thread, so it has its own state as well. So what we need to do is kind of pause the carrier thread and then take the state associated with the virtual thread and put it on the native structure that holds the carrier thread state. So what is happening is that, and this is how it works in OpenJDK, is that essentially you put basically a watermark on the stack and then build a new frame on top of the last frame of the carrier thread, and then resume execution there. And if the virtual thread had already existed, you'd be essentially copying that state on top. Now, it's not really a copy, it's more of a deserialize, because the virtual thread state is condensed into a structure that's more compact, so you're kind of expanding that structure back onto the native stack. And so once this process is complete, then for all intents and purposes, the virtual thread has become that thread that was originally the carrier thread. So the carrier thread object is held off to the side. It's still referenced to by the virtual thread, but when you query what that thread is, if you ask the thread, what thread are you? From that point on, it returns the virtual thread. If there's an exception thrown, it's going to show you the stack of the virtual thread. It's not going to show you the stack of the carrier thread. And then when a virtual thread blocks, we're essentially doing the opposite, where we're taking that state, we are serializing it, putting it into a compact form, and then saving it somewhere. And then once that process is complete, then we have unmounted the virtual thread. So this is how it works in OpenJDK. There's a lot of optimizations that I'm glossing over. It doesn't take the entire stack state. It only takes a few frames, because typically when you look at how this works in practice, you don't necessarily go down the full depth of the stack. A lot of computation is only done in the topmost frames. So you don't actually have to copy everything. You can take a shortcut and only copy the first few frames, and then lazily copy the remaining frames if you need it. Now, with OpenJ9, we do things slightly differently. So in OpenJDK, Java execution is done on the native stack. However, in OpenJ9, we don't use the native stack. We create a separate stack to execute Java code. And the reason for this was that it allowed us to grow the size of the Java stack. So if you think about when you allocate an OS thread, you need to allocate the size of the stack upfront. So I think typically on Linux x86, the default is going to be 1 megabyte. Regardless of what you're doing with that thread, you need to allocate the 1 meg. With J9, what we do is we allocate a small portion, and because we're not using the native stack, we can just reallocate a larger portion if we need more. So we start with a smaller stack and then grow as needed. But the fact that we're not using the native stack gives us a lot of flexibility, because what it means is that when we want to start a virtual thread or mount one, all we have to do is swap the stacks. So there's no movement of state. We're just swapping where the stack pointer is pointing. And so that makes this operation very fast. It's a few cycles. We're just shifting pointers around. And then when we're unmounting a virtual thread, same thing. We're just doing the swap the other way. So that's a little detail there on how the mounting and unmounting works with virtual threads. Now, there is a special case with respect to blocking where the virtual thread cannot be unmounted. So in this example, it's a similar example to what I showed you before, but instead of using a reentrant lock, we're going to use a regular object, and we're going to use the synchronize keyword. And so when you synchronize on a lock like this, because synchronization is an internal component of the JVM, it's very difficult to associate that state with a virtual thread. So what happens here is that as soon as you get to this point, the virtual thread is pinned to the carrier thread, meaning that the virtual thread cannot be unmounted. And so when the virtual thread waits, that means that carrier thread, the underlying OS thread, is also waiting. And so this can be the cause of throughput loss, because if this happens on many of your carrier threads, you've effectively limited your ability to execute any code there. Now, the good news is that in JDK 24, what I previously mentioned, this is true all the way up to JDK 23. This is exactly how it would behave. In JDK 24, however, the synchronization mechanism is being reworked such that now we have the ability to basically up-level synchronization. So take it out from the JVM and up-level how this works and associate it with the Java scheduler such that when a virtual thread blocks, we can take the virtual thread, unmount it, and add it to a queue that the function pool scheduler knows about, and that lock communicates with the queue. So when malloc becomes free, it notifies the queue, and then the virtual thread can be mounted again. So if you're using any of the previews or JDK 21 all the way to 23, this is the behavior where the virtual thread pins. Starting in JDK 24, which will be released later this month, this is no longer causes pinning. So pinning, as I said, occurs with synchronized blocks, but no longer in JDK 24. It also occurs with native calls. This restriction still exists, and it's probably going to exist for the foreseeable future. So when you call out to native, essentially what happens is you're transitioning from Java code to C or C++ code. And the compiler, the static compiler that compiled that code essentially manages the stack, where the variables are, etc. So as soon as you enter native code, it's very difficult to stop and resume because you need like in-depth knowledge of what the static compiler has done. So for this reason, native calls pin, and that means that as soon as you enter a native, the virtual thread is going to be pinned to the carrier thread, and it cannot be unmounted. And it can only be unmounted once it returns back into Java code. So this is another example of where pinning may occur. A lot of APIs, a lot of I/O APIs that originally would block in native code have been modified such that if it is a virtual thread, it detects this ahead of time and then blocks in Java code instead. So the cases where native calls are pinning, at least in the JDK, have been limited. Object wait, similar to synchronized. When you wait on an object, you first have to enter a synchronized block, and then you yield the lock. So pre-JDK24, this will cause pinning, but post-JDK24 and up, this no longer causes pinning. Class initialization is also a special case. When a class is loaded, only a single thread can load it. So if two threads need to make use of a class that hasn't been loaded yet, one thread is going to load it, and the other thread has to wait for the class to be loaded. So currently, this causes pinning because you're blocking, waiting for something to happen. And until it happens, you're going to be causing the carrier thread to be parked, essentially. There is some investigation into how this case can be resolved, but there's no support for this yet. This case is less common than the others. Typically, you do most of your class loading earlier on in the application lifecycle, and so it tends to not be a problem at steady state. So here is some best practices for using virtual threads. So in general, it's very useful for I/O-bound applications. So if your application is bound by its ability to basically connect to external resources, databases, sockets, that stuff, it's very useful because you can use the thread per request model, and as soon as it blocks, another task takes its place. One thing you should not do is pull virtual threads. Virtual threads themselves do not necessarily have a backing thread underneath. So if you pull them, you may risk starvation. If you want to limit access to a resource, instead of pulling them, you can use a semaphore or a managed executor. Those are better alternatives. And then synchronization pre-JDK24, again, is something you have to watch out for. It could cause performance degradation. If you're using JDK21, for example, and you're seeing a degradation due to synchronization, reinstrument locks is something that you can use instead. This does not cause pinning. So the virtual threads yield and remount as appropriately. Also, do not use thread locals with virtual threads. So thread locals is basically local storage for a thread. Given how numerous virtual threads can be, this means that you could be using a lot of memory. So instead, there's a new mechanism called scope values that allows you to share data between thread stack frames. And I'll talk about this later. All right, so now I want to spend a little bit of time taking a look at how virtual threads perform in practice. So as stated, I'm a JVM developer, so I'm often looking at things from a performance perspective. Some of my colleagues did an investigation last year, and looked at how virtual threads will perform if you use them as a drop-in replacement for an autonomic thread pool executor. So before I go further, I'll say the promise of virtual threads is not that they make things faster, is that they allow you to use the thread per request model effectively. So we weren't really expecting better performance. We just wanted to see if there was degradation, and if so, understand why. So for this experiment, Open Liberty was used. So for those who don't know, Open Liberty is a Java EE runtime. So it's designed for cloud-native development. It's a very lightweight Java EE runtime. It supports microprofile, Spring Boot, Jakarta EE, etc. So this is what was used for the experiment. So the experiment, there are a few applications used, but one of the main ones was online banking simulator. So it's a fairly good representation of a real application. It generates requests to a remote system, responds after a configurable delay. And because it has a delay, we ensure that the virtual threads are being unmounted and mounted again, just for more realistic understanding. Yeah, it's using functionalities like REST, microprofile, JDBC, etc. So the existing thread execution mechanism in Liberty is autonomic thread pool. And so this is a thread pool that actively manages the number of executors. So it doesn't have a fixed size of executors. It actively checks to see if the executors are doing work. If they are, and the performance is good, it keeps things as is. If there are some executors that are blocked, it adds more threads. If it noticed degradation because there's too much context switching, it removes threads. So it's actively managing and controlling the level of concurrency based on performance using historical records. So what was done with this experiment is we basically took that out and replaced it with virtual threads. So here are some of the results. So the first experiment was a throughput experiment. And so in this case, we were using a CPU-intensive workload. So we're basically seeing how many transactions per second can be completed given the number of CPUs. So in this experiment, we're using a 2-CPU configuration. And that's because a lot of the customers we work with, they're on cloud. They're deploying things on cloud deployments. And this is often a resource-constrained environment, so you don't have access to big 16 or 32 CPU machines. Typically, it's one box split up in ways. So we use the 2-CPU configuration just to get a good understanding of how it would respond in a constrained environment. So again, there's no expectation that virtual threads make things faster. We're just really looking to see if there's perf lost. So in this example here, we've got load driver threads. That's on the x-axis. So as you go to the right, we increase the load. And on the y-axis is a percentage of the highest score. So the highest score is at 40. And so everything else is a percentage of that score. And that score represents the throughputs, the transactions per second. So we can see the relative performance for each of those. So we see that at low loads, virtual threads performs well, even a little better. And then as the loads increase, we see degradation here. So the team did some investigation, and there are some probable causes. First of all, context switching for virtual threads is very fast, but it's not zero. So that's something that could be a contributor. As you make virtual threads, again, with virtual threads, it's a thread per task model, which means you're allocating a new thread each time. So potentially more GC activity might be contributing to this. One of the reasons that probably a bigger culprit is that in order to support virtual threads, some of the caching mechanisms that were previously used had to be disabled because they were using thread locals. And so there's a loss of thread local context with the virtual thread approach, and that probably has a bigger contributor. And then synchronization blocks, of course, can cause pinning. So those are things that were investigated. None of those were, we could say 100% this was the reason. One other reason is that virtual threads are using the fork join pool scheduler. And that's what we actually think is the biggest contributor. So I'll show you another experiment here. Here is ramp up experiments. So basically what's happening here is that the load is ramped up quickly in order to saturate all the CPUs. And we're basically looking for how quickly each of these configurations can respond to the load. So the experiment is done over 100 seconds. It's going from 0 to 6,000 requests and continuously offering more work. So as you can see here, again, same thing. We're doing a percentage of max throughput. And virtual threads responds very well here. It ramps up very quickly. Now, one of the reasons we suspect is that the pre-existing thread pool executor, it has a very controlled policy on how it adds threads. So with the virtual thread approach, as soon as you create it, it gets scheduled on the available executors, which is going to be equal to the number of CPUs. Whereas with the autonomic thread pool executor, it might be less. So we're not always going to max, and we don't get there as quickly. And so that likely explains why the ramp up is a little slower. And then here's another experiment. This time, instead of using the online banking simulator, it's using a simple microprofile primitive that just pings. So it's not doing much work here. This is a very thin application. And the load driver hits the endpoint, gets the result immediately. So this is just to see how it behaves in with very small application. So you can see the behavior here is similar to the first set of results I showed. And so this is where the team that determined that fork join pool scheduler might be the cause. As you can see here, with virtual threads, we tend to be around the 50% mark as the load increases. And so after more investigation, what was determined was that the fork join pool scheduler was parking one of its carrier threads for an extended period of time. And in this case, we're using a 2 CPU configuration, which means that you're effectively limited to 1 CPU. And that's why you're seeing it's kind of limited to the 50% range. So again, this is not really about virtual threads. It's more about the scheduler that is used with virtual threads. We played with some settings with fork join pool to tune it, but we never were able to get it to get to 100%. This is a similar test. Here in the y-axis, we're basically, so instead of just the throughput, CPU is shown as well, just to show the utilization. And what you're seeing here is the performance of virtual threads relative to the non-virtual threads case. So if you see 80%, for example, it means virtual threads are operating at 80% of the non-virtual threads case. So we see similar behavior. The general trend is that there's underutilization. So in the first example up there, that's done with the Linux kernel 4.18. So that's where we originally did the tests, and we noticed that the difference was much larger there. With the newer kernel, 6.2, the first one is done on RHEL 8. The second one is done on Ubuntu 22, 6.2. We see that the difference is less. There's still a bit of throughput degradation, but there's more CPU utilization. So the throughput degradation is less. So it seems like there's some interactions with the OS schedule as well that may cause a difference in performance. So Linux 6.6 introduces a new scheduler. We haven't tried that one yet, but it's on the list. And so maybe improves even further. So if you're interested in this experimentation, there's an article here that goes into it in a bit more detail and then shows all the findings, etc. All right, so now we'll move on to the next topic. So we'll talk about structured concurrency. So structured concurrency is a programming model that basically ensures that tasks run, start, and stop in a controlled manner. So within a structured scope. So this makes it easier to write concurrent code, makes it simple, safer, etc. So really what we're talking about is something like this. So imagine you have a thread of execution, and then you want to spin up multiple tasks, and then you want to make sure that everything, that your original thread proceeds after you've done that concurrent task. So that's essentially what we're talking about when we're talking about structured concurrency. So the threads, the forked threads, those are all contained in a structured task scope. And that's what controls the concurrency. So here's an example of how this looks like. So you have your thread. You create a structured task scope using the try with resources. And then you can fork tasks. And this is how you increase the concurrency of the application. Once you've done that, then you join on the scope, and it just waits for all the subtasks to complete. And then you proceed. So it's fairly simple. There are different types of structured task scopes. So the one I showed you is the basic one. There's others that basically allow you to short circuit common cases. So if you want to stop all units of execution as soon as there's a failure, then you'd use the shutdown on failure scope. And if you want to stop as soon as one of the threads succeeds, then you'd use the shutdown on success. Now, you can create a structured task scope within a structured task scope. And so when that happens, you end up with a tree that looks like this. So you can continue to propagate these as far as you want and then join them back. You can also shut down structured task scope. But if you do so, what it does is it shuts down all the child scopes as well. So again, this is not a very detailed overview of structured concurrency, but it gives you a general idea of how this works. One thing I should mention is that when you use this API, it creates virtual threads. So these are not platform threads, these are virtual threads, lightweight threads. So they're very cheap, and that's what makes this feature a very useful feature, because you can simplify the model and just fan out and fan in as you need. Okay, and lastly, we'll look at scoped values. So a scoped value is essentially a value that can be shared between methods. So there are cases where you want to share some data between methods, and you don't want to pass that data as a parameter for all intermediary methods. You may not even have access to those intermediary methods, but you want that data to be propagated to a method that will be called in the future. So these are the cases where you'd want to use scoped value. In the past, a lot of people have used thread locals for this reason. So one of the goals is that this will replace thread locals eventually. This mechanism is an easy mechanism to use. It has a bounded lifetime, so unlike thread locals where you have to explicitly free that memory, these ones have a bounded lifetime. It's built into the way you use it. You can use existing access control mechanisms to control who has access to this data. So it's not a free-for-all where anyone can access it. And there is a per-thread cache state that makes it fast to look up. So here's an example of how to create a scoped value. So at the top, we're going to create a scoped value name, and it's essentially a string. We're going to bind that string to Devnexus, and then when we call that method, when that method looks up name, it sees Devnexus. And then in the second example here, we can rebind that name to a different string, and the same thing. When it sees that name, in the second example, it sees loon. And then there's a different variation of this API where you call a method that returns a value instead. So that's the basic usage. The API does change in JDK 24, so it is slightly different, but overall it's the same idea. So here is how you can use scoped values with a structured task scope. So you can create a structured scope value, and then within it, create a structured task scope where you have parallel execution. And so each of those tasks now see the same scoped value. And once you've finished execution, you free the memory associated, the string object associated with that scoped value. So this is how you get the bounded lifetime. So overall, if we do a comparison between scoped values and thread locals, scoped values have built-in memory management because their lifetime is bounded. Whereas thread locals, there's always a risk that you might have a memory leak if you forget to free that memory. Scoped values are immutable. So once you bind them, they're bound within that scope, and they can't be changed. So you don't have data inconsistency if you have multiple threads changing things. Multiple functions changing things. Thread locals cannot be used with structured task scopes, so there's a limitation there. And when you create a platform thread, when a child platform thread is created, it inherits all the thread locals from its parents. So it copies all the thread locals from its parents. And so what this means is that if you have a thread creating many threads, you're propagating those thread locals, which uses a lot more memory. In this case, with scoped values, they're all sharing the same underlying memory. So if you create a tree of concurrency, you're not expanding the number of values. It's still the same values, and it's all being shared by all the children tasks. So some limitations. Scoped values are intended to be used in small quantities, especially if you're using it with a structured task scope. So there is a cache. Every scope has a cache associated with it, so it doesn't have to walk all the way up to its to the super scope to find the scoped value. However, if you make a lot, then you exhaust the cache, and then you have to walk all the way up. There is an option to expand the size of the cache, but that also means you have to sacrifice memory usage. And again, not intended for legacy threading models. So if you're using a thread pool, this is not a mechanism that's suitable for that. So yeah, this concludes my talk on virtual threads. Hope you've enjoyed it. I can take any questions now, if there's any. Yeah.
You made the statement that virtual threads are about making the usage of the, what word you used, the platform thread more efficient, not necessarily faster.
Yeah.
So when would I want to use a virtual thread over just using the platform thread? I think maybe is a piece that I'm missing.
Okay, yeah. So virtual threads is really about the thread per task programming model. So if you want to write very simple concurrent applications, virtual threads is a very powerful mechanism for doing so. In the example I showed with the performance comparison, this is the thread pool executor is executor that's been around for many years. It's been tuned for many years. It's a highly optimal executor. So it is, depending on what your goals are, if you're writing a new application and you just want to write simple concurrent code, then virtual threads is for you. If you have an existing application and you're thinking, should I migrate my concurrent model to virtual threads, then it's a different kind of question. You probably have to do experimentation to see what the trade-offs are. You may not be getting more performance, you may be getting less. It's kind of what I'm trying to say.
And then further, I think you were talking about the structured concurrency and the structured task scope. So are those sort of like workers that run on the virtual threads?
So if we go back here, so the structured task scope is you can think of it as a scope that manages virtual threads. So when you create a structured task scope and you fork tasks, each of those tasks is a new virtual thread, and they're all managed within the structured task scope. Yeah. Yeah, no worries. You can take any other questions? All right. If not, I'll be at booth 19 if you want to discuss about JVMs in general. I'm happy to talk to you. And otherwise, thanks for joining my presentation and enjoy the rest of your day.